Okay, so right now we're going to learn about reaction kinetics. And the first thing we want to do is go over a few of the grade 11 things that we've learned about. And the first one is exothermic reactions. So in exothermic reactions, energy is released. An example of this could be something like gasoline burning, paper burning. Often energy is a product, and we see here on this reaction right here that energy is on the product side. So reactants produce products plus energy, and if we were to graph this, the reactants would have an energy level that is way up here, and then on this y-axis would be our energy, and then whence this reaction starts to proceed, we see that energy is lost in the reactants, and it goes down, and then it becomes products. Now the products have less potential energy, and this energy that is right about here is released as heat energy, which is different from an endothermic reaction where it needs to absorb energy. So reactants need to absorb energy in order to become products. So reactants have an energy that is way down here, and then it will often absorb energy, and when it absorbs energy, then it can become a product. Okay? And this means that the delta H, or in other words, the change in enthalpy, remember grade 11, delta H, delta means change, H is the measure of enthalpy, this is going to be a negative number. And the change in enthalpy for an endothermic reaction is going to be a positive number. So, how to calculate the change in enthalpy? Well, the change in heat is going to equal the heat contents of the products minus the heat contents of the reactants. So again, change in enthalpy is equal to the heat content of the products minus the heat content of the reactants. So for here, we see that this number, whatever it is going to be equal to on the y-axis here, is going to be here, and this number is going to be way over here. So if this number was 10, then this number is going to be maybe 50, and our change in enthalpy will be 10 minus 50, which will give us a negative number. And over here on an endothermic reaction, if this was 10 and this was 50, it'll be 50 minus 10, which will give us a positive number, or in other words, in this example, positive 40. Okay, so it's a very easy calculation. Change in enthalpy is products minus reactants. Now moving on. We're going to talk a little bit about reaction kinetics now and factors that affect the rates of reaction. So first thing is how to calculate reaction rate. Before we start talking about the things that affect the reaction rate, let's talk about how to calculate a reaction rate. Calculating reaction rate is about the amount of products formed divided by a specific time interval. Reaction rates will vary as a reaction proceeds. They might be very fast at the beginning and then slowing down later at the end. And so we have to make sure that a specific time interval is done. And it can be the amount of products formed over a time interval, or it can be the amount of reactants used over a time interval. Now, this will form the same reaction rate because of the conservation law of mass. So we can use either one can be used to calculate the reaction rate. Now, this can just be summarized as having reaction rate as being the change in the amount, and it can be either the amount of products formed or the amount of reactants used, and divided by the change in time. Now, let's do a quick little example here of a reaction have here, it says 22 grams of a reactant is used in 4 minutes. So what is the reaction rate in grams per second? So what we can do is we can just simply go 22.0 grams of reactant is used, and it says, can't really read it now, is 4 in over 4 minutes. So we're going to divide this by 4.0 minutes. Okay, now a very simple calculation. We're going to multiply this by 1 minute, which is equal to 60 seconds. Now, if we do this calculation, we end up with a number like 0.092 grams per second. Now, just to make sure that our units are correct, we look at here and we see minutes, and this cancels with this minutes, and all we're left with is the grams per seconds. This is 3 significant figures divided by 2 significant figures multiplied by a definition, or in other words, something with no sig figs. So 3 sig figs, 2 sig figs, our final answer should have 2 significant figures, which it does. Okay, and it's the right unit because our units cancelled. Now, moving on, let's do a little bit of a different one, a little bit harder one. So if we're given the reaction aluminum plus chlorine gas, it gives us aluminum chloride. It is found that chlorine is consumed at a rate of 0.2485 grams per second. Calculate the total mass of aluminum chloride produced if this rate is maintained for 3 minutes. So I like to start with something that we know. So it gives us, in this question, the rate of consumption, which happens to be 0.2485 grams per second. Okay, and that's 0.2485 grams of chlorine. So I'm going to write that part of my equation. Now, first thing I want to do is change this into moles of chlorine per second. So I'm going to change this to moles of chlorine by multiplying by 1 mole over the molar mass of chlorine gas. So chlorine gas, chlorine is 35.5, but since there's 2 of them, it's going to be 35.5 times 2, which is 71.0 grams. Okay, and then I'm going to use my molar ratio, which is a 2 to 3 ratio, and I'm going to multiply that to change this into moles of aluminum chloride. So there's 2 aluminum chloride for every 3 chlorine gas. So now my unit is moles of aluminum chloride per second. And now I want to change this into grams of aluminum chloride. So I'm going to multiply this by the molar mass of aluminum chloride. Aluminum is 27, again chlorine is 35.5. 35.5 times 3 plus 27 for the molar mass of aluminum, and that should equal about 133.5 grams, and that's per mole. Okay. Now, what we have here is a rate is maintained for 3 minutes. So 3 minutes, which is also equal to 180 seconds. Now we can just multiply this by 180 seconds. Now, as we see here, this 3.00 minutes, this is 3 significant figures, so I'm going to put a little dot right there to signify that this is 1, 2, 3 sig figs. Okay? and this is going to equal 56.07 grams of aluminum chloride. Now let's just go back over our problem. As we see here, we have 4 sig figs divided by 3 sig figs multiplied and divided by an exact number, multiplied again by 4 sig figs multiplied by 3 sig figs. So the smallest amount of sig figs that we're using here is 3 sig figs. So using the multiplying dividing rule, our answer should be in 3 sig figs. And here our answer is 4 sig figs. We need to change this into 3 sig figs. So it should be 56.1 grams of aluminum chloride. And this would be our final answer. Okay? Now, I want you to get a little bit of practice by working on page 2 in your workbook of Hebden and do questions 1 to 5. Okay? Good.